Next speaker, David Carfì. Title of the talk, Algebraic and Geometric Methods in Schwartz Distribution Spaces for Relativistic Quantum Mechanics. Please.
Thank you very much. Good afternoon to everyone. And I, first of all, express my great pleasure to be here. And hopefully we will see again each other in presence in Ukraine. Good. My talk is an application of Schwartz linear algebra, which is a methodology, of a geometric and algebraic methodology to study both the Schwartz distribution spaces and quantum mechanics. In particular, Schwartz linear algebra makes very simple some treatments of relativistic quantum mechanics. Well, the approach, well, provides an efficient justification for the use of many quantum mechanics mathematical tools. Why? Because Schwartz linear algebra uses bases, bona fide bases, constructed and capable to generate the entire space of temporal distributions and more generally the spaces of Schwartz distributions. And it provides us the possibility to define again the coordinate operators and so the possibility to construct manifolds modeled on distribution spaces which have, well, manifolds which have tangent spaces endowed with bases, with tangent vectors bases. So I show you the application, and by the way, I will give you some hints about Schwartz linear algebra. But first of all, I say you that the fundamental features are two, and the operation of superposition, which is a kind of integral, a generalized integral, which indeed was suggested by Laurent Schwartz in his great treatise of analysis about distributions. So let's see the paper. First of all, we consider the relativistic Hamiltonian here. The relativistic Hamiltonian is a function from R to n into R. And the function is defined on a, position momentum space, if you want, by a square root. So we had a problem in Hilbert spaces because not only the square roots of an operator is not always effective operation in Hilbert spaces, but we have had problems in Hilbert spaces because the position and momentum operators corresponding to position and momentum in the Hamiltonian formulation of quantum mechanics and of mechanics in general. Well, the two fundamental operators are not continuous, and that is a great problem. Well, in the space of temporal distributions, we can define continuous linear operators, and so we can use again the basic concepts and basic properties which we use in finite dimensional linear algebra and finite dimensional differential geometry, and also in finite dimensional analysis. So the basic point is this one. This is one of the failure in Schrödinger to translate into quantum mechanics the concept of Hamiltonian, relativistic Hamiltonian. As we know, Schrödinger tried to translate in operators the follow this function, but he failed because Hilbert spaces cannot handle with this functions. As you will see, in space of temporal distributions, we can handle very simply with this function, and we can finally define the operator corresponding to this function, to the Einstein's Hamiltonian of a relativistic particle. And moreover, our operators will be continuous, linear and continuous operators. So, these are only notations, and I want only to underline that we shall use this version of the Hamiltonian. So not anymore in a Hamiltonian in the position momentum space, but only in the four momentum space, the Einstein's four momentum space. So E over C is the energy over the divided by the speed of light, and P is the three momentum, the usual three momentum. So our function, Hamiltonian function, will be defined so, as you can see, by C multiplied by the square root of the modulus of the three vector P plus m0 c squared. P0 squared is m0 c squared. M0 c squared, both of them. Okay, so we have the Euclidean norm of the four vector P0P, four vector in the sense of a linear algebra, not in the sense of tensors or Minkowski setting, and multiplied by C. Moreover, the Schwartz distribution theory allows us to understand properly, both the roles played by Euclidean norms and Minkowski norms, where when Minkowski norms are invariant, we have an Euclidean counterpart, which is the, the variable, the dynamical variable. For example, in this case, we have a duality. On one hand, we have the Hamiltonian function and then the Hamiltonian operator. On the other hand, if you use the Minkowski norm of the corresponding four momentum, you obtain M0C, which is an invariant of the system, such as M0 c squared. So, using this form of the Hamiltonian, we can define, and that is the most important contribution of our paper, we can define the corresponding operator in quantum mechanics. More and more, okay. This is the definition, quantization of the relativistic Hamiltonian. So we define the Hamiltonian operator H hat from S prime M4 into S prime M4 in the following way. First of all, S prime is the space of temporal distributions defined upon the Minkowski four space. So we have an operator corresponding to our function, previous function H, and this operator is everywhere defined. This is the first gaining in our play. We have an everywhere defined operator. So for every possible temporal distribution defined upon the Minkowski force space, we have a result, we have a value of the operator. The definition is the following one. We use the Schwartz integral, the generalized Schwartz integral, that, by the way, I recall you the definition of this generalized superposition operator, and it is simply the composition of a temporal distribution with an operator associated with a family of temporal distributions. Well, the basic, as I just told you, the basis of Schwartz linear algebra is the presence in our spaces of algebraic bases in some sense. Such bases are continuous spaces. Look at that. We have the basis beta equal to beta p, with P belonging to P4. P4 is the Minkowski space of momentum, of 4 momenta. So we have a continuous basis, a continuous family of distributions. We need all the temporal distributions, de Broglie waves. These are the Broglie waves. As you see, we have one wave for each P. P is a 4 vector, and we have the components of this 4 vector presented here in the 3 momentum P and the energy component E. So we use the Schwartz integral and the continuous basis of de Broglie waves to construct the Hamiltonian operator for the relativistic particle. The relativistic Hamiltonian is here, is the function h, and h hat is the operator associated with this Hamiltonian. As you can see, simply I must say that H is the system of eigenvalues of the Hamiltonian operator, of this new Hamiltonian operator, with respect to this basis beta. So we have simply the integral with respect to beta as a generalized distribution, generalized distribution, regular distribution, because it's a family of distributions. And with respect to the distribution, the usual distribution, H times this psi beta. I will define psi beta, the very important concept from a geometric point of view and algebraic point of view. Psi beta is the system of components of psi, of the vector psi, the infinite dimensional vector psi, with respect to the infinite dimensional basis of de Broglie waves. So it is, you can see here, we can indeed, as in finite dimensional algebraic methods, or in linear algebra, we have the vector psi is the superposition, is the, infinite continuous sum of the de Broglie beta, the de Broglie family beta, with respect to this temporal distribution. So this is the implicit definition of the temporal distribution psi beta. And obviously, you can, with algebraic and geometric methods, very naturally prove that this psi beta, this system of components, is uniquely defined by the vector psi and the basis beta. And here we have again your reminder for what is the Schwartz generalized integral. Is the composition of this temporal distribution psi beta with the operator associated, as you see here, and you can see also here, the operator associated to the Broglie family. Well, the definition of the operator associated to the Broglie family is here. So you have all of the full picture, and the beta hat is a continuous linear operator from SM4, the space of Schwartz rapidly decreasing functions from M4 to C, to the complex plane, into the space of Schwartz rapidly decreasing functions on the momentum, on the four momentum Minkowski space. And the definition is very natural. It just reminds us some definitions from the tangent spaces of differential manifolds. We simply say that the function beta hat of phi, which is the image of phi under beta hat, calculated at P, is nothing but the value of the temporal distribution beta p on the function phi, for every phi belonging to the space of Schwartz on M4, and P obviously belonging to the four momentum space. So we have the definition finally of the operator associated with the square root of P squared plus M0 C squared, the Schrödinger problem in Hilbert spaces. Here we have the answer, the definitive answer in the space of temporal distributions. We have a linear continuous operator. So let's continue with our paper. Well, those are technical parts. Now I want to show you the first properties of the Hamiltonian operators, the principal properties of the Hamiltonian operator. So we can see relatively simply that the relativistic Hamiltonian operator H hat, just defined, reveals the unique linear continuous operator on the space of temporal distributions defined on the Minkowski space M4, sending each de Broglie wave beta p to the temporal distribution HP times beta p. HP, what is HP? HP is the square root of p squared modulus p squared plus M0 c squared times the speed of light. That is not a problem. So it is, well, it is a function, a smooth function times beta p, which is a temporal distribution. So in other terms, we are saying that simply beta p is one eigenvector, a bona fide, a proper eigenvector of the operator H hat, and the corresponding eigenvalue is HP. Well, is the function H calculated at P. So we are saying only that H hat is the unique linear continuous operator on the space of temporal distributions, which has beta p as a system of eigenvectors and HP the system of eigenvalues corresponding to beta p. Well, when P is varying in P4. Okay, moreover, H hat reveals Schwartz diagonalizable. Well, in what sense? In the sense that there exists a Schwartz basis of the space constituted by eigenvector, and the Schwartz basis is just seen the de Broglie wave basis. Moreover, the H, the operator, reveals regular and Hermitian in the Schwartz sense. You can ask me, what is the sense of regular and Hermitian? After all, in a space which is not a Hilbert space? Well, in the sense that the operator H is the natural extension in the distributional sense of a function, an operator, a continuous linear operator defined on the Schwartz function, rapidly decreasing function space, and the natural extension in the sense, well, you know, how we extend the derivative from the space of functions to distributions and so on. So H hat reveals the extension of a regular Hermitian operator in the Schwartz function space. And the function space of Schwartz is a subset of L2, which is a Hilbert space. So we have a Hilbert product, and we can say if one operator, especially where continuous operator, is Hermitian or not. So one of the basic properties of this operator is its Hermitian property. Well, that is proved here. I don't want to prove this, well, but we have another, well, now our application, I have, I think, 5 minutes to explain the application or not. Please, Chairman, I have 5 minutes, 3 minutes. Have I?
5.
Thank you very much. So our Schrödinger equation in the space of temperature distribution is simply IH bar d over dt, well, psi equal h hat psi. So we can finally define the general relativistic Schrödinger equation by using our new operator, the operator of the relativistic Hamiltonian. Well, and here we have simply the derivative operator in the space of temperature distribution, so with respect to time, so nothing complicated. All is standard. I show you only the definition of momentum, well, momentum operator, which is obviously linear and continuous because the derivative operators in the space of temperature distributions are continuous, besides linear. And this is the definition of the operator P, which obviously intervenes in the definition of H. And well, here we have the energy operator, but this is not very important. Go to the solution space of the Schrödinger equation. Let's go. So define the energy operator, which is nothing more than the derivative with respect to time times IH bar. Well, we have the simple form of the Schrödinger equation as E hat psi equal H hat psi. So the energy operator, which is a derivative with respect to time, is equal to H hat psi, which is the square root in the distribution sense of, well, of a Euclidean, if you want, a Euclidean norm of a four operator in the classic sense. Indeed, you have nothing more than the square root of c squared p squared operator p plus m0 c squared identity operator on the space of temperature distributions. Unfortunately, I have not here the formula, but it's clear. It's absolutely clear. So we introduce a partial family of the de Broglie space. This partial family wants that the energy component of our four momenta should be the value of the Hamiltonian, relativistic Hamiltonian H calculated at the 3-vector P. So we have HP over C P as 4-vector. I just remind you that the general beta has P 4P, a 4-vector P, which is E over CP, not HP over CP. So we have restricted our de Broglie wave family to another family. We consider a restriction of the family beta, and we obtain a new family, well, chi, a family chi. We shall use this family chi to solve our Schrödinger equation, and I show you immediately the last theorem of my talk. So let EH be the relativistic Schrödinger equation corresponding to the relativistic Hamiltonian H. Then we see that the closed subspace of the solutions, which is closed because the relativistic, our relativistic Schrödinger equation is a continuous linear equation. And so we have the closed subspace of solutions is generated, generated by the family H, restricted from the de Broglie wave family. And here you have the de Broglie wave. Indeed, the solution space of the Schrödinger equation is the solution of the distribution division problem E minus H psi beta equal 0. Well, I comment only this. This is the most important point. We have reconducted our resolution of the relativistic Schrödinger equation to a division problem in distribution space, obviously. And this division problem, so find the distribution A such that the multiplication of the E minus H times A is equal to 0. So the solution A of this problem, division problem, are nothing more than the system of components of the solution psi with respect to the de Broglie family. So this is, as you can understand, the most important result. I reconducted a complicated Schrödinger equation EH with an operator in which we should use the square root of continuous operators in distribution spaces to a simple division problem. And here we have the solution of that division problem. We have, it is the closure with respect to the usual topologies of the vector space generated by all the Dirac distributions centered at the graph G, which is explained in the next page, plus a singular, very singular term generated by the derivative of this, as you see, the derivative of the Dirac delta, and the component of the energy component is nothing more the relativistic invariant M0C of the beginning of our talk. So, well, I thank you very much, and for the questions, thank you. Thank you for your attention and patience. Thank you.
Thank you very much.